Good afternoon, everyone. This is the pre-launch news conference for TDRS-L, the tracking and data relay satellite to be launched aboard an Atlas V rocket this coming Thursday night. And here to talk about TDRS and the TDRS network is Badri Yunus, the Deputy Associate Administrator for the Space Communications and Navigation System at the NASA Human Exploration and Operations Mission Directorate at NASA headquarters in Washington. Tim Dunn, the NASA Launch Director from the Kennedy Space Center. Vernon Thorpe, the Program Manager for NASA missions from the United Launch Alliance. Jeffrey Gramling, the NASA TDRS-K Project Manager from NASA's Goddard Space Flight Center. Andy Capito, the Civil Space Programs Director for Boeing Space and Intelligence Systems. And Clay Flynn, the Launch Weather Officer from the 45th Weather Squadron Department of the Air Force at Cape Canaveral Air Force Station. And we'll begin first with comments from Badri Yunus. Badri?
Thank you, George. Good afternoon, everyone. I am Badri Yunus. I am the Deputy Associate Administrator responsible for all of NASA space communication and navigation. What do these networks do? They provide connectivity to anything that's flying in our solar system and even beyond. We have three separate networks that have evolved independently one from the other over the past 50 years. They have been old, they needed some replenishment, they needed some new technology to advance the capabilities. I was hired by NASA a few years ago to do so. And not only to fix what needed to be fixed, but also to introduce the new capabilities that will advance the data rate by orders of magnitude to what we have been having. And while meeting our present commitment, it's a world-class service we provide to our users. We need to maintain this while building for the future. And so early on, we focused on identifying the problem, defining the architecture through 2025, and defining the technology that we needed to focus on. We have made a lot of progress. We evolved the technology. We are already in the implementation phase. The technologies that we focused on are advanced and robust communication protocols. We worked hard on advancing the RF related technology to move us to bandwidths that can support much higher data rate in the Ka band. We advanced the optical communication, laser communication from far away, as we recently demonstrated from the moon through the LADI mission. We had a small payload, 10 centimeter wide aperture, communicating at 622 megabit per second direct to ground. We also advanced the software-defined radios and the cognitive radios. This is the last time we hardwire our communication system when we send them in space. We are, we are wiring them through software, the kind of things that you can update, you can reconfigure on the fly, and you can fix problems while you are on your way to accomplish your mission. In the past, hardwired radios couldn't be afforded this luxury, and you had to live with the way you implemented back then. So I'm going to show you a presentation on a few slides on our notional architecture and how are we meeting our timeline over the next few years. We start with 2015, where we are going to still provide the kind of capabilities that have evolved so far, but we are adding to it the communication aspect. Now we are all of our capabilities will become network-based capabilities, providing network-based services. We are moving away from big dishes to support deep space mission in favor of equivalent arrays of smaller aperture antennas arrayed together to provide you not only the same performance, but much better performance for our deep space mission. And as I said, we already tested our optical payload, and we succeeded. We had instantaneous acquisition from the moon to the ground at 622 megabit per second. And also, we proceeded to replenish our constellation of data relay satellites. Last year, we flew TDRS-K. This year, and with the help of ULA and the help of Goddard, our Goddard team, and Boeing, we are going to hopefully succeed in launching TDRS-L. By 2018, the technology will have evolved more, with more of it, and more capabilities have been put into operation. We are going to take the optical communication an extra step. We are going to place it on a data relay satellite and demonstrate the feasibility of this technology from a data relay satellite orbiting Earth. We are going to move up in the data rate by providing 4 times the data rate we are providing in the RF domain through the capabilities we've evolved to maximize the gain we can get out of the Ka band. And we are going to potentially have a lunar payload to provide data relaying capability from around the moon. By 2023, we'll continue to replenish the TDRS constellation with another data relay satellite to be known as TDRS-M. And hopefully this will give us enough capability on orbit to meet I always forget this. To meet NASA's needs as well as those of our partners. And we'll also, and I'm keeping my fingers crossed, we'll introduce optical communication in deep space, potentially providing streaming video from the surface of Mars. I know everybody and everyone is looking forward to that. And by 2025, much of this technology will have been fully implemented. Much of the new capabilities will be in place to allow us to have robust space internetworking throughout the entire solar system. And we'll make decision what to do with the 70-meter antennas that we have in our deep space network, to potentially retire them from communication, but to dedicate them for other objectives. And we'll have made complete conversion from the analog domain to the digital domain. Again, we are striding and working very hard to reduce the cost of communications to NASA and ultimately to the taxpayers, while increasing the capability by orders of magnitude. You know, our scientists have been aspiring to the kind of bandwidth we can bring to use for so many years. It took some wise decisions within NASA to go in this direction and to find the limited fund that allowed it to move forward. So what's in it for the taxpayers? Definitely better science data, but also all of the technology that we evolve at NASA get transferred to the commercial sector. So commercial users will have to look forward to all of these advances in technology, because definitely they are going to be the primary user of these new technologies. I'll be happy to answer any question later on. Thank you.
All right, thank you, Badri. And now to Tim Dunn, who is the NASA Launch Director from the Launch Services Program from the Kennedy Space Center, about Thursday night's launch and our launch preparations. Tim?
Thank you, George. I'm proud to be here today representing the men and women of NASA's Launch Services Program, and I'm thrilled to be the launch director for the TDRS-L mission. The voice and data communications that the TDRS constellation brings back to Earth every day from the International Space Station, the Hubble Space Telescope, and many of our on-orbit NASA science spacecraft touch each of our lives. Working alongside our United Launch Alliance colleagues, the engineers and analysts of NASA LSP take great pride in launching TDRS-L. NASA has a terrific record flying on Atlas V. We've successfully launched 10 missions on this rocket, missions to Pluto, Jupiter, the Moon, the Sun, the radiation belts, and 3 spacecraft to Mars. TDRS-L will be the 11th NASA mission on Atlas V and the 43rd Atlas V launch overall. TDRS-L will launch on an Atlas V 401 vehicle from Space Launch Complex 41. Slick 41 is proud to have hosted 35 Atlas V launches to date. Now I'd like to show a video of the ULA crew receiving and assembling the Atlas V launch vehicle and mating the TDRS-L spacecraft at Slick 41. Please roll the tape. Here you see the arrival 2 months ago at Port Canaveral of the TDRS-L first stage booster and second stage Centaur. These Atlas V stages are manufactured at ULA's state-of-the-art factory in Decatur, Alabama in the beautiful Tennessee River Valley and then transported to Cape Canaveral via this ship named Mariner. Here you see offload from the Mariner and transport across Cape Canaveral Air Force Station to the Atlas Spaceflight Operations Center, or ASOC, for pre-launch processing. Here is early morning in December, mid-December. We were rolling out the first stage booster to the Vertical Integration Facility, or VIF, near Slick 41. What you'll see is the erection sequence and placement on the mobile launch platform of the first stage booster. This occurred on the morning of December 13th. You have a nice view of the first stage engine of the booster. That's the RD Amros RD-180 engine with a thrust of 861,000 pounds. You'll see the very methodical lift sequence onto the mobile launch platform in the VIF. Here is the rollout the next morning, December 14th, of the second stage Centaur and moving out to the VIF for its erection and mate sequence. You see a very controlled lift here of the Centaur. You see a nice view of the RL-10 engine on the aft end of Centaur. That's the Aerojet Rocketdyne RL-10 with a thrust of 21,900 pounds. You see the mate to the top of the first stage booster in the VIF, and there's a nice view of the completed stack in the vertical integration facility. Just a few weeks ago, on the morning of January 13th, we rolled the encapsulated assembly out to the VIF for mating to the top of the Centaur. The encapsulated TDRS-L spacecraft in its payload fairing was lifted mid-morning on January 13th for its mate sequence. And you see mating there to the boat tail at the top of the Centaur. And there is the completed stack that we look forward to taking out to the pad for launch. The TDRS-L launch campaign has gone very well. Over the past week since TDRS-L mate, the Atlas V team has been busy with launch preparations. Last Wednesday, we performed the final integrated systems test with the spacecraft and rocket. Last Thursday, we performed a successful mission dress rehearsal to exercise and prepare the entire ULA, NASA, and Air Force launch team. Then last Friday, the combined NASA and ULA launch team held our Flight Readiness Review, or FRR, where we assessed all processing and pre-launch preparations for the mission. Just this morning, we conducted the Launch Readiness Review for the TDRS-L mission. Senior managers from NASA KSC, Goddard Space Flight Center, and NASA headquarters, as well as ULA and the Air Force, assessed the readiness of the rocket, the TDRS-L spacecraft, and range assets to proceed with launch on Thursday evening. Tomorrow, we will begin our final launch preparations at approximately 10 a.m. Eastern Time by rolling the Atlas V on its mobile launch platform approximately 1/4 mile from the VIF to the launch pad at Slick 41, and then filling the first stage fuel tank with highly refined kerosene, or RP1. On Thursday, the launch crew will begin arriving on console during the afternoon hours Eastern Time. The crew will perform final preparations of Atlas V power on and electrical checks beginning approximately 2 p.m. This will be followed later in the afternoon by loading the super cold or cryogenic propellants on board. First, liquid oxygen will be loaded into the tanks of the first stage booster and the second stage Centaur. Then liquid hydrogen will be loaded into the second stage Centaur tank. Final flight control tests will be performed along with final tests with Eastern Range instrumentation, and then we'll be ready for launch Thursday evening at 9:05 Eastern Time with a 40-minute launch window. To summarize, the Atlas V rocket and range equipment is ready, and the combined government and contractor team is prepared. We're all excited to launch this critical national asset, the TDRS-L satellite. Back to you, George.
Thank you, Tim. And now to Vernon Thorpe, the program manager for NASA missions from United Launch Alliance. Vernon?
Hey, thanks, George. Good afternoon, everyone. United Launch Alliance is honored to be here again 2 days before launch of the TDRS-L satellite. I saw some of you just 2 months ago when we launched the Maven spacecraft to Mars, and a year ago when we launched the TDRS-K satellite for NASA. Our ULA team started working with NASA to integrate this latest generation of TDRS spacecraft onto Atlas a little more than 4 years ago, and we began building the vehicle for this particular launch about 2 years ago in Decatur, Alabama. As always, our ULA team has worked very closely with NASA, the spacecraft team, and our other mission partners to get us to this day. And it's been a tremendous team effort as usual. We look forward to a great launch on Thursday evening. As we were preparing for this press conference, I realized that Atlas and the TDRS program have really been supporting each other for about 20 years. The second generation of TDRS, the 3 spacecraft that are currently known as TDRS 8, 9, and 10, were all launched on Atlas IIA vehicles. I think one of those was in 2000 and 2 of those were in 2002. So it's great to be back here launching the next generation. But while we were integrating the second generation, this was back in the late 1990s. At that time, we also developed a new TDRS-compatible transmitter for our Atlas launch vehicle so that Atlas could actually use the TDRS system to relay telemetry during flight. And that has worked out wonderfully. And in fact, at ULA, we've actually implemented that TDRS compatibility on our Delta II and Delta IV vehicles as well. That ends up giving us a lot more flexibility in our trajectory design. It helps us save some cost. We don't have to arrange for as many ground stations, for example, to cover us. And I think it's a great testament to the breadth of valuable services that the overall TDRS constellation provides. As Tim mentioned, this will be our 43rd Atlas V mission. It'll be our first launch of the year, ULA's first launch of the year. And it'll be the 78th ULA launch in just over 7 years. And this year we have a very busy manifest. In 2014, we've currently got 15 launches planned. 10 of those will be from down here at the Cape. I think 4 of those are for our NASA Launch Services customer, 2 Atlases and 2 Deltas. So some of those will be out of Vandenberg. And we've actually got 5 missions for NASA if you count the Delta IV Heavy that we're going to use to conduct a test launch for the Space Exploration Program later this year in September. The specific Atlas V configuration that we're going to use for TDRS-L is an Atlas V 401. That's using our 4-meter payload fairing. And as Tim mentioned, we're going to use the RD-Amros RD-180 engine on the first stage. And we'll use an Aerojet Rocketdyne RL-10A-4 model engine on the upper stage. And for this mission, we do not require any solid rocket boosters. So I think Tim did a great job in explaining how we've gotten to this point with the launch vehicle manufacturing and processing and putting it out on the pad. Now I'd like to roll a video that will show you what we expect to see on Thursday evening, starting at liftoff. Can we roll that tape? So here's our 401 configuration on the pad. And for this vehicle, since we have no solid rocket boosters, the first major event that you'll see after liftoff will occur about 4 minutes in. And that's when we deplete all the propellants in the booster tank and we separate that first stage from the Centaur upper stage. You'll see something very similar to what you're seeing right here on Thursday night. You can see the booster stage increasing in altitude, and in a moment you'll see that engine shut down 4 minutes into flight. When that happens, we fire some retro rockets. We separate the Centaur upper stage about 6 seconds later. We'll spend about 10 seconds flowing cryogenic propellants through the engine before we light it on the upper stage to condition the engine, and then we'll actually light the engine. That will be for the first of 2 engine burns, upper stage engine burns for this mission. 8 seconds into that first burn, we'll jettison the payload fairing. And that first engine burn will last almost 14 minutes. I think 13 minutes, 55 seconds is our current prediction. After that first engine burn, we'll coast. We've got a fairly long coast, about 1 hour and 20 minutes, and that will put us in position for a second burn. That second burn you see here will be pretty short, just over a minute. And at that point, the stack will be in a geosynchronous transfer orbit. We'll spend a few minutes reorienting to the right separation attitude. We'll separate the spacecraft as you see there. That will happen about 1 hour and 46 minutes into flight. And then after we do that separation event, we'll do the normal collision and contamination avoidance maneuvers to put our Centaur upper stage into a disposal orbit that won't interfere with any other spacecraft. So total mission duration will be about 2 hours for this. As usual, we are proud to serve a critical role in delivering payloads to orbit for all of our government customers, and we're focused on perfect product delivery for this and every mission we launch. We try to maintain a relentless focus on delivering critical capabilities to orbit, and I think TDRS-L is a good example of that. Delivering TDRS-L to orbit will complement the overall constellation. It'll continue our legacy, and it'll enhance NASA's ability to communicate with the space station and with numerous other spacecraft orbiting the Earth. And I'd like to say thank you once again to all of our partners who helped make this happen. And the entire ULA team looks forward to a great launch on Thursday. Back to you, George.
Thank you, Vern. Now it's Jeffrey Gramling, the NASA TDRS-K project manager from NASA's Goddard Space Flight Center. Jeff?
All right, well, thank you, George. We're thrilled to be back here a little less than a year after we launched TDRS-K. For those of you that were around last year, you'll remember that we had a beautiful launch right at the beginning of the window. Launch went great, put us in a great orbit, and I think we finished up on-orbit testing in the June timeframe. I'd like to thank ULA and the Kennedy folks for giving us a great launch, and of course our partner Boeing here for giving us a great satellite, which has been drifted to its operational location and has supported users since we put it into operation. As you've heard before, this is our second launch in our KLM program. Our first 7 launches, TDRS 1 through 7, were launched on the space shuttle, and then as you heard Vern point out, we launched HIJ, K, and now L on Atlas vehicles. So we've had a great experience with Atlas. Right now, I've got some video to show you the processing flow since we've been at the Cape, so we can go ahead and roll the video, please. All right, I think this is maybe back on January 5th. We flew on a C-17 from Boeing's factory in El Segundo, California. The plane left Los Angeles Airport, landed here in the morning, early morning hours. You can see the shipping container coming off the C-17 and then being rolled over to processing facilities at Astrotech in Titusville. And while we're at Astrotech, there's some spacecraft testing that gets done, and then the spacecraft gets fueled before we encapsulate and bring it to the vertical integration facility here at Kennedy. So here you're seeing the spacecraft coming out of the shipping container. In this configuration, the single access reflectors are furled and remain that way through launch until shortly after separation from the Centaur. Right here, the spacecraft is vertical and placed on a test fixture. Of course, then the testing happened, the spacecraft is fueled, and here you see the two halves of the launch vehicle fairing, which are about to swallow up the spacecraft. And you can see that the spacecraft kind of fits very neatly in the fairing there. We're pretty snug, but we've got room for our dynamic loads. And then the whole encapsulated spacecraft and the fairing will be placed on a vehicle to take us out to the launch pad, or to be raised up into the vertical integration facility to be placed on top of the launch vehicle, which you saw earlier. And I believe this happened Sunday before last, in the or early morning hours of Monday, when the roads were empty. All right. And then Tim's video kind of picked it up from that point, and you saw it get lifted and placed on top of the launch vehicle. So the next little animation we've got to show you is what happens after separation from the Centaur, to pick up with the video that Vern just showed you. So here you can see us, we're separated. The SA reflectors get unfurled about 2 hours after we separate. We've got 5 burns we do using an engine which is integrated into the spacecraft. That over the course of 10 days, that will raise our orbit up to geosynchronous. And then once we're there, then we would do deployments. And this whole phase is operated out of Boeing's Mission Control Center in El Segundo, California. So here you can see the single access reflector booms being deployed. You've already seen one of the solar arrays being deployed. The next solar array, and then the forward Omni, and then the space to ground link antenna that points to our ground station in White Sands, New Mexico. Once the deployments have been completed on orbit, then we would hand over from Boeing's control center in California to our control center in White Sands, New Mexico. And then here's just a nice animation showing a day in the life of a TDRS constellation, basically to kind of give you an idea of how busy the TDRS spacecraft are on a day in and day out basis. So that was the last video I had. Thank you. Back to you, George.
All right. Thank you, Jeff. Now to Andy Capito from the Civil Space Programs at Boeing Space and Intelligence Systems, our director for TDRS-K. Andy?
Thank you. On July 28th, 1958, NASA was founded. Boeing has been working shoulder to shoulder with NASA on programs critical to the nation since the very beginning. First slide, please. Our Boeing unit in El Segundo constructed the Surveyor landers, which made soft landers on the moon in the 60s. In the 70s, Boeing supported the Apollo program, including development of the legendary lunar rovers. And in the 80s, Boeing's Rockwell division was responsible for development of the Space Shuttle orbiters, recently retired, which continue to inspire young people to careers in the space industry. Next slide, please. Today, Boeing is proud to continue this legacy by supporting NASA's critical mission to lead the world in space exploration. With recently modernized technology, NASA astronauts on the International Space Station can transmit and receive voice, video, and data delivered through a state-of-the-art Boeing-provided communication system. The signals from the International Space Station, Hubble Space Telescope, and other Earth-orbiting satellites are relayed up to geosynchronous orbit, 22,000 miles above the surface of the Earth. These satellites are received by the TDRS satellites, where they are amplified and relayed to Earth. On Thursday, we will be launching TDRS-L, the 5th of 6 TDRS satellites to be constructed at Boeing's Satellite Development Center in El Segundo, California. Next slide. The Boeing TDRS series, shown here undergoing antenna deployment testing, is notable for the large 15-foot single-axis antennas, which lock on and track platforms in low Earth orbit. This performance is impressive. Remember that TDRS satellite will be orbiting the Earth over 22,000 miles above the equator. The platforms they communicate with are in orbits typically 300 to 600 miles above the Earth. This means that the TDRS satellite must track an object over 22,000 miles away that is moving across the face of the Earth roughly every 45 minutes. This capability is analogous to standing at the top of the Empire State Building and tracking an ant as it marches its way down the sidewalk in front of the building. A truly remarkable capability. Next slide. The TDRS-L launch campaign started with our arrival aboard a Boeing-built C-17 cargo aircraft. The shipping container was unloaded and brought to nearby Astrotech facility for processing. At Astrotech, the state of health of the satellite was successfully verified. Once given a clean state of health, approximately 1,700 kilograms of propellant was loaded on the satellite. The satellite will consume approximately 1,500 kilograms of propellant to maneuver itself from transfer orbit provided by the Atlas launch vehicle up to geosynchronous orbit. The remaining fuel will be used to maintain the satellite's orbital position throughout its greater than 15-year mission lifetime. Next slide, please. Once transferred to the Kennedy Space Flight Center, the TDRS-L satellite was encapsulated in the Atlas launch vehicle fairing, as we've seen. This operation marked the start of combined operations with the satellite team supporting ongoing launch vehicle activities. Once encapsulated inside the launch vehicle fairing, 3 important activities were performed. All connections between the launch vehicle and the satellite were fully tested. The batteries are carefully maintained and then charged for the last time prior to launch. The satellite will remain on internal battery power through the launch phase of the mission through satellite separation. The satellite will continue to be powered on batteries until after separation, when the satellite can orient its solar panels to the sun. The RF telemetry system of the satellite is also verified for the last time during this phase. This is important since TDRS satellite will be launched with its telemetry transmitters off, and they will be turned on automatically after separation from the launch vehicle. Next slide. After acquisition of satellite signals, the TDRS-L satellite will be flown from the Boeing Mission Control Center in El Segundo, California. Control will continue from the Mission Control Center through the trans-orbit circularization period and through the initial on-orbit checkout. In-orbit testing of the satellite will be conducted from White Sands Testing Facility in New Mexico until final acceptance of the satellite by our NASA customer. Next slide. Boeing is very excited to have NASA as our customer. We look forward to supporting projects like Commercial Crew Vehicle and Space Launch System in the years ahead. I'd like to conclude by quoting Jim Lovell. There are people who make things happen. There are people who watch things happen. And there are people who wonder what happened. To be successful, you need to be a person who makes things happen. At Boeing, we look forward to making things happen for our NASA customer for another 50 years and beyond. Thank you. George.
Thank you, Andy. And now for a look at the weather forecast for Thursday night. Clay Flynn, the launch weather officer for TDRS-L from the 45th Weather Squadron, Department of the Air Force at Cape Canaveral Air Force Station. Glenn?
Thank you, George. The weather looks favorable for Thursday evening's launch count. If I may have a satellite picture, please, at this time. If you'll look really over the peninsula of Florida, there's a frontal boundary, a cold front to the north. You can see that through the cloud cover there over the peninsula. That front should be migrating, or will be migrating to the south, should pass central Florida over us this evening, a couple of hours after sunset. Behind that front, in advance of the front and actually behind the front, the winds do pick up a little bit. The pressure gradient tightens. We'll look for winds to get a little strong at a couple hundred feet, gusting in the mid-20s, perhaps upper 20s during the overnight hours. So a little breezy tomorrow for MLP roll, but below the roll constraints. High pressure begins to build in behind that front tomorrow, and would expect to see those winds trending down through the day as high pressure builds in with fair weather. for the launch count on Thursday, the weather continues to be favorable as high pressure noses down the peninsula. The pressure gradient's relatively light, so the wind shouldn't be that strong. We'd be looking for winds out of the north gusting to about 16 knots. Those are all at a couple hundred feet. There's a front to the north in Georgia about the time we enter the window. It introduces a little mid-level moisture in advance of that front over us, but a relatively small threat of any type of thick cloud violation. So again, the weather looks pretty favorable for a Thursday evening launch count. In the event of a 24-hour delay, that front pushes down to the south, should be through us during the overnight hours, late morning hours. Leaves a little residual moisture over us, so a little increase in moisture with a small threat of a thick cloud violation, probably a little more significant. Behind that front is the pressure gradient does tighten a bit, which would give us stronger winds. Wind should be out of the north gusting to about 22 knots, still below the liftoff constraint. So again, weather favorable on for a Friday attempt, should we be attempting on Friday. Thank you, George.
All right, thank you, Clay. And now we're ready to take questions. Please give your name and affiliation when the microphone comes to you. We'll start here in the front with Marcia.
Marcia Dunn, Associated Press, with a few questions for Mr. Gramling. How long will checkout last? And given your current status of your network, when would you expect this TDRS to go operational?
As we usually do, on-orbit checkout takes between 3 and 4 months, and then that'll probably take us into the May timeframe, I think, and then we would drift to our operational location. I believe we're going to maybe 49 with this one, so in the eastern position. So those are roughly the time frames we're talking about.
And when would you expect to need it, given your current circumstances? And one more question. I see that both TDRS-K and L with the White Sands mods were about $715 million. Can I just divide by half and get the cost of the satellite, or is there something a little trickier to compute?
Yeah, I think you can roughly do that. The modifications to our White Sands ground station are in there as well, but those are small compared to the spacecraft cost, so you're in the right ballpark. I'm sorry, in your first question?
Operational. I mean, what's your game plan? Thanks.
So let's see. Right now, as you know, we've got several spacecraft in service. So I believe the intent would be to put this into storage first order. You know, depending on the health of the existing constellation. You know, once we get to the point where we finished on-orbit testing and we have some more information about the health of the on-orbit fleet, then that decision may be revisited, but I think that's the current plan right now. We've been fortunate. We've had spacecraft that are doing pretty well, and we've got K that we just put into the fleet. So,
additional questions? James?
James Dean, Florida Today. Jeffrey or maybe Andy, is there any way you could quantify sort of the amount of data relayed each day in sort of everyday terms, movies, videos, you know, things like that? I mean, just the flow of data in a way that people kind of relate to. So
I wish we actually had a little bit more of that last animation I showed you, showing the amount of contacts per day. But so basically in each of the 3 positions, we've got 2 TDRS satellites that are in service. So that's 6 satellites in service, basically at any given point in time during the day, and we're supporting several spacecraft, Hubble Space Telescope, space station, launch vehicles, Earth observation spacecraft. Each of our SA antennas, we can operate right now at 300 megabits. I don't know that each of our user spacecraft is operating at 300 megabits, but that gives you roughly the capability of each SA antenna. So, I mean, that gives you an idea. I don't know that there's a lot of idle time in our on-orbit fleet. We're generally supporting users all the time. So the system is pretty heavily used. If you're looking for more specifics, we can probably try to get those for you. But
not all of the users have the same data rate. You have different types of users. So you are talking about in the tens of thousands of hours per month combination between all of the data relay satellites.
So just kind of following up on that, these satellites are described as a national asset, a critical lifeline. We understand ISS and Hubble are in the picture among many others. I mean, can you just, to underscore the significance of these things, which may not be super obvious to the average person, I mean, could you imagine perhaps if TDRS just evaporated and we didn't have it, maybe you went back to 40 years ago and just had your ground stations or something, what would be the impact of that day to day? I mean, in terms of not being able to communicate with humans on ISS or the science data we could get back versus what we can get now.
Yeah, with the TDRS, what we have is continuous support for anything that's flying below geosynchronous orbit. Without which you'll rely on dispersed ground station that could be located anywhere around the globe. Given the political map, the places where we can be are very limited. So instead of getting the 100% coverage that we are obtaining now with TDRS, not only we are getting global coverage 100% of the time, we are getting it in real time, So without such support, we'll have to live with very limited coverage around the 10 to 15%. So no human space flight program can be supported at this data rate, and even our our ability to respond in real time to emergency will diminish drastically. So the TDRS, that's why the TDRS has been declared as a national asset, because of not only the kind of capability it brought to bear, but our ability to reach any point on Earth in real time, 24/7.
Irene?
Thanks very much. Irene Klautz with Reuters. I just wanted to first verify that with this launch, there'll be 7 TDRS satellites in orbit, operational orbits. And I wanted to know what percentage of the TDRS capabilities does the DoD still use? And also, what are the plans for TDRS beyond this 3rd generation? You touched on this a little bit in your opening comments, but I wasn't clear if these plans for like optical comm and so forth are actually already into some like pre-contract description, or where that stands. Thanks.
Yeah, our architecture relies on 6 operational spacecraft and 1 hot spare. We definitely cater, and these are designed to primarily support the NASA mission, but on occasion we do support other government entities, to include also other space agencies from elsewhere, as long as we have the capacity. The need for so many spacecraft is driven by the geographical location, not the capacity per se. So given that we need so many data relay satellite to be located around the geosynchronous orbit, we can afford, because we are left with some additional capacity on each data relay satellite, to support other users. DoD's support, we respond to the priority of the country, so on occasion we may be called upon to provide that support. It varies. I cannot give you a certain percentage because it's not constant. It depends on what's going on, what needs to be supported. The same way NASA does go to DoD networks and primarily Air Force network to get support from the various ground stations that are located worldwide. The TDRS is a system that has been developed with taxpayers' dollars, so it caters to the interests of the country, to be that national interest or economic interest. Looking at the future, and as I said earlier, we have been trying to advance the capabilities on board. The cost per spacecraft is a little bit large, based on the state of the economy. So I've been trying to drive the cost down. at least 50%, if not better. And by also trying to introduce new capabilities such as optical communications and other software-defined and cognitive radios, to possibly going after the bus itself and trying to get something that's so modular that you can design and launch as needed, carrying only the communication capabilities that you need, or short of. We have a program in place to advance the technology and test it and validate it for operational use. We started by demonstrating that we can do it, and we did it. Next stage is that how easy is it to operate it in space, especially when you have so many users flying around and you are trying to point to a particular user and acquire the signal coming from that user. It takes some time to get familiarity and operational familiarity in particular. So we are putting this payload on board a commercial bus around 2017 to allow us about 2 to 3 years of testing and to see, how easy it is and what do we need to do to the technology to optimize it. Once we complete that, we are ready for operation. So we have gone beyond now we are going beyond the level 6 in terms of technology readiness, and we are, navigating through the 7 and 8, and hopefully the 9 will be happening soon. We started to commercialize component of the commercial payload, so it's already being transferred to the commercial sector as I speak. Definitely, the benefit of optical communication also will be best, felt in deep space. So we are working with our friends at JPL to advance that technology, and we are looking for a ride, most probably in the early 20s, to have a laser communication payload on board a deep space mission, most probably a Mars orbiter. Then I can meet the promise I made a few years ago to provide streaming video from Mars. Did I answer all of your questions?
Thanks. Just one quick follow-up on the current contract with Boeing. So Boeing is also building the TDRS-M, and NASA is not going to exercise. I believe there originally was an option for a third-generation satellite. And did I hear you say right that M is launched like in 2023 or some crazy year?
The capacity that we build is definitely driven by present and future requirement as estimated requirements. Sometimes you can nail your requirement 5 or 10, a few years down the road, but to look so way deep down, it's hard to quantify them. So we built, we had a contract with Boeing for essentially 2 spacecraft, KNL, with option to buy more. Now, when we talked about the cost earlier and the number that was quoted, much of the money here is really for the first copy, non-recurrent engineering, because later copies come at much cheaper price. We determined with the extension of the space stations, life expectancy, as well as other requirements, that we need TDRS through the 2030. So we quantified our requirement, and we determined M will definitely be critical to our future operation in the early 2020s. Now, and we looked at the cost benefit of procuring M early, even though we won't need it until the early 2020s. We did not want to wait so many more years and have to pay additional non-recurrent engineering and the extra cost it may require to procure a new spacecraft. We said by exercising M, we get the cost benefit here of an exact copy, that we may later, probably later, we may not be able to afford. So it was a smart decision by NASA, knowing very well that the need for such a spacecraft is critical in the early 2020. So now we have the flexibility of launching at any time So if the requirement increase in the next few years, we'll launch it a little bit earlier than planned. But I don't need it operationally until the early 2020s. Sure.
Bill?
Bill Harwood, CBS. Just two quick space station TDRS questions. And the first one I should know, and I'm not sure. Are there any gaps at all in coverage, or is it 100% with KU and S-band, or are there time periods in the orbit when you have one or the other but not both? I'm just curious. And the second question is related. What percentage of the network bandwidth, the total network, does ISS account for, if there's even a ballpark number? I don't have any idea.
You know, I'm going to give you answers not extremely accurate, but close. It's 100% of the, you know, of the time we provide support to the International Space Station. We provide it through primarily 2 data relay satellites, you know, taking care of much of the orbit, with the exception of a small sliver, you know, that facing Guam, that where we had to add additional capabilities to close on the 100% coverage. So that's why I can say, yeah, we provide 100% of the coverage. How much the percentage depends on the activity in and around the space station. When you talk about the space station alone, we provide a dedicated, almost a dedicated TDRS to it. Now, when we have other activities, launch vehicle, you know, or visiting vehicle, we have to, you know, assign other TDRSs to provide that support. But does not mean only a single TDRS. I'm talking equivalent of a TDRS, you know. So it's like 1/6 of the capability.
Thanks. That's what I
remember. You know, obviously, it takes them time to hand over from one spacecraft to another. So,
All right. Have we any additional questions? Irene, follow up.
Here's another question. I was wondering if there are any commercial users of TDRS. A long time ago, there was actually, I think, a dedicated transponder that was put out for a commercial bid, and kind of lost the storyline on that.
We definitely have some commercial entities. You just heard that the Atlas Centaur, which is a commercial entity, depends on TDRS for its support. TDRS is the primary support for all launch activities that takes place here within the United States. We also, because of the limited capacity and the increased requirement we have, in the past, we had plans to commercialize some of the services, but because of the need, the government-owned need, was overwhelming, that we had to build additional data relay satellite. We could not embark on that because, you know, our priority is what these satellites were built for, our own missions as well as other government priorities.
Did you answer Bill's question about how much of the TDRS network is ISS responsible for? Like, what's the load on TDRS just from ISS, and is that increasing because of the new commercial payloads and non-NASA things that are flying on station?
Again, the space station alone is about 1/6 of the capability. That goes up every time we have visiting vehicles. So the support around it increases, but not, you know, from within. The way we try to meet the needs of the space station by increasing the data rate, the capability on board. And so most probably, once we deploy the demonstration for you know, an optical or a laser data relaying capability, we are going to have a laser on board the station to test with, and then, you know, it may remain there, and the space station may end up the first user of optical capability that will be provided in the future. And then you are talking gigabits per second, unlimited.
Okay, James, a follow-up?
James, Vern, it was mentioned that this TDRS-L is a pretty snug fit in the fairing. I was just curious if it's one of the larger vehicles that you fit in your fairings by size, if not mass.
It's one of the larger in terms of the volume it takes up, but you know, that volume's not a solid mass. It's pretty diffuse. It's mainly the mesh antennas. back in the Atlas 2 days, we actually stretched our 4-meter fairing 3 feet to accommodate that second generation of TDRS. And that was basically a 3-foot plug that we put into the cylindrical section of the fairing. And that's what we're using again for this generation of TDRS as well. So yeah, if you just look at the exterior outline of the spacecraft, it probably fills the 4-meter fairing up the most of about anything we fly in that particular fairing. Most things don't extend up into the conical section as much as these satellites do.
Any further questions? All right, in that event, that will conclude the briefing, and we're going to go out by showing you a video and animation on the TDRS system and the TDRS Space Communications Network. Thank you very much.
In the late 1970s, satellites such as the Nimbus 7 satellite relied on NASA's ground stations located around the world to provide a communication network. This ground-based network could only provide communication over 15% of the satellite's orbit. With its ever-expanding orbiting fleet of satellites and manned spaceflights, NASA had to increase the coverage and develop an improved way to track and communicate. In 1983, NASA launched the first of a series of new communication and navigation satellites that would rely less on international ground stations and provide continuous coverage. Tracking and Data Relay Satellites, TDRS, are a network of geosynchronous communication satellites that work in conjunction with 2 ground stations. Today, NASA's fleet of spacecraft and launch vehicles, like the Tropical Rainfall Measuring Mission, TRMM, can communicate and navigate with the help of TDRS. This interaction between TDRS and the spacecraft is a series of complicated signals that guarantees that every Earth-orbiting spacecraft will have nearly non-stop coverage. The International Space Station, ISS, routes voice and video communications along with data through the TDRS fleet. The Hubble Space Telescope also utilizes the full capabilities of TDRS. TDRS supports the Hubble's real-time interactions with the ground systems, allowing observers to make small adjustments to its observatory system. TDRS provides the Earth observing system of satellites, such as the Aura spacecraft, with low-latency data relay and navigation data. The TDRS network sends all of these data streams and voice communications to either the White Sands complex in New Mexico or the Guam Remote Ground Terminal. Guam then transmits the data it receives to White Sands. The White Sands complex then relays it to the end user at their missions operations centers. As long as there's space exploration, TDRS will be working side by side with spacecraft and end user, providing continuous connectivity for navigation, data, and voice communications.